Okay, hello, welcome to my channel. My name is Solo Anch, and in this video we want to prove this important property of scalar product of three vectors. So given three vectors A, B, and C, they want to show that distributivity property holds, okay? And we're not going to do the usual algebraic way. We're going to use geometry, okay? So we're just going to make use of this figure. And also we're going to make use of concepts from projection of vectors, okay, which we've done in our previous video. And if you haven't watched that, you may have to, okay. But if you have an idea about projection of vectors, we are good to go. And if you find this video helpful, please don't forget to subscribe to my channel and then share this video with your friends, okay. It's a way of encouraging me to make videos like this. Good. So let's analyze the diagram a little bit. Okay, so we have the three vectors that we need, vector A, B, and C. Okay, so if vector A starts from point O to point A, vector B from point O to B, and then vector C from point B to C. And then you could also observe that these lines from B, M, that's line B, M, and line C, and are perpendicular to the direction of vector A. Okay, so I don't know if you're thinking about it right now, but what I want you to think about right now is that the length of this line from O to M, all right, could be thought of as the scalar projection of vector B, which is a vector from point O to point B, scalar projection from what we did in our previous video. So that's why it's important to go back there to look at it if you haven't, all right, or maybe you've forgotten a few things. Then you can also think about the length of line MN as a scalar projection of vector C, which is a vector from point B to point C. And then lastly, the length of line from O to N as a scalar projection of a vector from point O to point C. So maybe let me just put those down. Okay, so I just want to put down two of them. So I would say that the length, that is the length of these lines, OM and O and MN, are the scalar projections vectors from OB and to BC respectively. Good. Okay, so from what we understand scalar projections as, okay, that's nice. Now we may want to we may observe that is clearly what vector from O to C is. That is a vector from O to C. Well, from O to C, we could easily just add these two vectors, right? That is, we could say vector OC is the same thing as a vector from O to B plus the vector from B to C. But what is the vector from O to B? We have that to be vector B, and the vector from B to C is vector C, which tells us that the vector from O to C is simply B plus C. Okay, so let's look at the left-hand side of what we want to show. We want to show that, by the way, I forgot to mention, where I got the proof is from Mathematical Physics by Gupta, right? It's a popular book, so you could check that out. Okay, that's where I got this proof. All right, so let's continue. That is B plus vector C. That's the left-hand side of what we want to show. Okay, now, you know that we've established that the sum of these two vectors, sum of vector B and C, is just that is the vector starting from point O to point C, which is B plus C, right? Okay, so using that, and then recalling that we could rewrite, when we have the dot product of two vectors, we could write it as this. We could write it as the length of the first vector, that's the length of vector A. Okay, we could take it as the length of vector A times the scalar projection, so permit me to just write that, of the second vector, that is vector OC, onto vector A, that is in the direction of vector A. Okay, so maybe let me just go back there. That's from the previous video, which I advise you go back to. So let me just put it out here. Where is it? Excuse me. Okay, this is it. So I were able to establish that if you have the dot product of two vectors, we could simply take it as the length of the first vector times, all right, the scalar projection of the second vector, which in this case is B, in the direction of that first vector, and we were able to figure out that the scalar projection of vector b in the direction of vector a is given as the unit vector pointing in the direction of vector a dotted with that vector b. Good. So using that right here, we'll have that to be the length of vector a, which we can simply just write it as that, times the unit vector, okay, pointing in the direction of vector a, then we dot that with the vector OC. So I will just say vector OC, the scalar projection, right? Okay. Well, let me just put it down just for completeness. We dot that with vector A divided by its length. Good. Okay, that's nice. But this right here is given from the diagram. We can observe this. From the diagram, we see that the scalar projection of vector from O to C, okay, in the direction of vector A is simply the length from O to N. All right, so that means I'm just going to multiply the length of vector A by the length of this line from O to N, because that's simply the portion of vector C pointing the direction of vector A, or you can say the length of the shadow. Maybe just kind of a very informal explanation to that. That's length from O to N. Good. So this is not a vector because we're looking at scalar projection is just a length. Okay, maybe let's continue from there in the next page. So this will give us, well, let's see what is the length ON. We can split it as a sum of two lengths. We can split it as a length from O to M and then plus M to N. So that's OM plus MN, right? So that will be the length of vector A times, all right, the sum of these two lengths OM then MN, which we could simply distribute. Why can we distribute? Well, we could distribute because these are just numbers. Okay, this is the length of a line, this is the length of another line. The sum is a real number, so we could distribute when we have numbers. So I'll just take the length of vector A. I think this notation is bulky. I could simply just write A without anything on it, just to simplify or just to reduce how much I write, isn't it? So let me just make that to demarcate. Okay, so let's get back to the figure. Good. Now, what is this? Remember, recall that OM is the scalar projection of vector O from O to B, which is vector B. And then similarly, MN is the scalar projection of a vector from point B to point C. So maybe you can kind of reverse the order of our computation, okay? Or you can think about it this way. From this understanding that the dot product of two vectors is the length of the first vector times the scalar projection of the second vector in the direction of the first. So since this is the length of the first vector times the scalar projection of the second vector in the direction of the first. So what is the second vector? We look at the figure. The second vector here is vector from point O to B, which is vector B. The projection in the direction of the first vector, which is vector A, is OM. And then similarly, the second vector in the second sum, or that is the second term, will be the vector C, which is whose projection is MN in the direction of the first vector, vector A. So that means we could simply write this as a dot product. That is, as I said, the reverse order. The dot product, that is A, times the original vector, where this is the projection, where this is the scalar projection, and that original vector is a vector from point B, from point O to point B. Maybe you want to look at that one more time. From O to B, the scalar projection is OM. Then this will be from B to C, whose scalar projection is MN. So maybe let's just put that down. So that will be the length of vector A. Sorry, I'm writing everything now as the dot product of two vectors. That is the length of vector A times from B to C. But of course, we know what these are. The vector from O to B is simply vector B. Then from B to C is simply vector C. So maybe let's just put that down. This is vector B plus that, then vector C. Sorry, vector C. Okay, dot vector C. So what did we start off with? On the left hand side, we have this. So that tells us that the distributivity property works. Okay, is simply A dot B plus A dot C. So that is a very, very nice result, all right? So we've been able to establish that simply by using this figure and then the idea from scalar projection of a vector onto another vector. I hope this video was helpful. We're going to pause here because we've gotten what we wanted. In the next video, we'll just continue and exploring some beautiful properties of vector products. All right. Okay. Thanks for watching. Please share this video with your friends, and we'll continue from our next video.